Okay, class, welcome to our next lecture from chapter 3. We're on topic 2, global extrema. And so we're gonna, just again, quick visualization. So we've got our surface here, and we're looking for the global extrema. In this case, here's a global max. And then there, it looks like if the surface sort of ends right here on this book edge, there would be infinitely many global min at the what is kind of like the XY plane here. But what we're going to be doing is doing this over a particular region. So use this little cord here to sort of cut off a particular section. Maybe it comes right through here, in which case then the global extrema defined over this region R would be global max here. And there are probably many ties for global mins down along this edge. Okay, so that's our visualization. And now we're going to move on to figure out how we're going to do that algebraically besides just looking at a surface. So if we're given an algebraic expression of the surface, so today I want to work on these. There's actually two examples here. We want to find the global extrema for this surface. Clearly lives in R3, clearly nonlinear, because the squares and the multiplication interaction terms. And we will always be given a region over which we want to find these global extrema. And so this is what makes the two problems. The first problem, use this region, which is a rectangular region. The second one, use this region, which we'll get to that. We see it's got some sort of nonlinearity to it, but we'll get to that in a moment. Before we get there though, let's actually review some things that we remember from R2. Because as usual, much of what you remember from R2 will help you in R3 and higher. So over here in R2, if you wanted to find global extrema, there was this theorem that we used. Remember the extreme value theorem? That's how you found extrema on a closed interval. And so if your function was, f had to be continuous, which just means you could trace it without picking up your pencil off the paper. So most Calc 1 problems are always well-behaved, continuous. So something like this. And then you had a closed interval. So there are two conditions for the extreme value theorem. If these conditions hold, so if your function is continuous and then they gave you an interval over which you're interested. We don't want the global extrema from minus infinity to infinity or whatever the entire domain is. They always give you like blinders for the graph. So they would give you maybe an A and a B, and you had to find on this section of the graph, what is the global min, global max, or if they're ties, that was also possible. The EVT told you if these two conditions hold, then you were guaranteed at least one global min, at least one global max on that interval. And hopefully, again, the key thing from the EVT was an existence theorem, told you whether it was worth your time to go hunt for those extrema. But the useful thing when you were actually solving for global extrema algebraically was to find this phrase, was that global extrema occur at two places. CPs and EPs. So EP stands for the endpoints of your interval, and that's your A and B. Have to have a closed interval, have to include the endpoints. So right, we couldn't have open dots here. That would be open or half open. So we needed the interval to include its endpoints. And then the global extrema, these are the only things you had to do is check. Make a list. Often you did something like this. You put any CPs you had. It looks like there's one CP right here. We'll maybe call that C. And then you put your EPs. As long as the CPs fell within that interval, you put those. So we have two EPs, one at the left endpoint A, one at the right endpoint. And those were your X values. And then what did you plug in? Did you plug this into the F prime? Or did you plug it into F? So hopefully you remember that it was the function. And why does that make sense? We wouldn't plug that into the derivative. We'd plug it into the function because think about global extrema. Highest or lowest on the graph. You're looking for the smallest or tallest as y goes, and there's my smallest. There's my tallest right there. So you always plugged into your function and then you just looked in this list and decided who was the tallest, had the greatest y value, who was the smallest, had the smallest y value. And those were your global extrema on that interval. Okay, so we're gonna have something very, very similar in this section. We're gonna have a similar theorem and a similar method for attacking to find these global extrema. Before we do that though, let's get a visual on what this thing looks like. So you can pause the video at the same and do the same thing that I'm about to do, just to check your tech tool skills. So pause the video and graph this surface. That's the first thing. Catch up with me on this, and I'm going to share my screen, and we'll get to the same place in a moment. Okay. All right, so I'm in Calc-Plot 3D, and I'm going to enter this surface down here at the bottom, x squared plus xy. That's the surface we're interested in. And hopefully you could tell already from that algebraic expression of the function that there was some nonlinearity and what it might look like. And let's come over here to the surface and see. Hopefully you recognize that it has this saddle nature to it just by the algebraic expression, but then you see it when we rotate it about. So we have a saddle point in the middle there, and then we'll rise from those up to the sides. Okay, we want to look at the first one, or the region 1. We want to find the global extrema on the closed region from x equal -2 to 2, y -1 to 1, so this rectangular interval. And I want to show you another feature here in Calc-Plot 3D. So you can do something called select a region. And we're going to do this a couple times in class, also in chapter 4. And so the preset one here is this parabola, but we don't want that. We want to go from y. The y limits are from -1 to 1, so the top one will be 1, -1 on the bottom. And let's just put our, and our x range goes from -2 to 2. I'm going to turn off the function x squared plus xy, and we're going to go back to our region here and enter x squared plus xy, and that'll be what we call the top function. The bottom function will leave at 0, and you'll see why here when I turn it on. Okay, so this defines the that hyperbolic parabola, that surface right here. So you see that, and then let me zoom in a bit. Yeah. All right, this is the part. Let me go turn that one off again and go back to our original. This is just the section of that hyperbolic paraboloid. This one is defined over a much bigger region. Same surface, but now when we restrict it to be over this rectangular region that we're interested in, and you see the rectangle in the bottom, as x goes from -2 to 2, here's our x equal -2, x equal 2 over here, y from -1 to +1. So it creates this rectangle in the bottom over which we want to define the surface. And that is now rotated about. You can now see the sections of that saddle. What's interesting to see is, yeah, there was like the saddle point in the middle here, but when we go just a little bit to one side, we're actually, you see these dips below the xy plane. So these are negative z values down there. And on this section, you can now use a tool like Calc-Plot 3D to visualize where these global extrema occur. So again, we are restricting the section over which our surface lives. I mean, think about R. R will always live in the xy plane, and then it's going to go from the xy plane to the surface, and that might be going up to the surface or down to the surface. In this case, largely we're going up to the surface, x squared plus xy, and we can again get an idea that it looks like our global mins are down here, one here, and then because of the symmetry of this function, there's one on the other side, this guy over here. And then the global max, we can zoom out a bit, we see that there's going to be, looks like also because of symmetry, possibly a tie. Yeah, there's the way we can see the symmetry of a tie. There's a global max and a global max defined over this region. We just have to now figure out exactly where they are. And you can, from the graph, kind of get a pretty good idea. It looks like over here at y equals 1, x equals 2, we'll go up to this particular z value. And then diagonally across, this would be at, let's see, x equals -2 and y equals +1, it looks like over here. So we have a pretty good idea visually where our global extrema should happen, and we'll be able to check that. Okay, the next region I want to show you with Calc-Plot 3D. So the picture will look very different when we restrict ourselves to be over region 2. Unfortunately, though, we can't use this select add a region to do region 2 because region 2 is quite a bit different. So maybe let me stop screen sharing for a moment and just graph these 2 regions over here. Region 1, easy, that's in the XY plane, -2, 1, including all the endpoints. So we have this boundary that we are including because less than or equals. And then everything inside that, right? So that's region 1. On the other hand, region 2 is y equals -square root of x. That looks like this, right? Y equals -square root of x, only from x equals 0 to 3. So region 2 is actually just this line, this second segment of the line, this nonlinear line. So region 2, quite a bit different from region 1. And because it's not like 2-dimensional as this one is, we can't use that same feature in CalcPlot 3D, but we can still use CalcPlot 3D to look at it. So let's share the screen again, back to CalcPlot 3D. So now I'm going to go back to just the surface, which we had here. And then we're going to graph y equals square root of x, and I'm going to do it as an implicit function to make sure it remembers it's in 3D here. So y equals -square root x, and we wanted x to go, the one we're really interested in is that x is from 0 to 3. All right, so then let's zoom in a bit. And hopefully you know that this y equals square root of x has a free variable z, so it's going to be a vertical wall, but it'll be bent, right? It's got a curve to it, nonlinearity, and it'll come up and down. And when we zoom in and look from the top, we see, okay, there is the region R2 over which we only care about the part of this paraboloid that actually lives over that, which in this case turns out to just be the intersection of this purple with this sort of pinkish, peachish color here, right? And so we're now just have, rather than a 3D region, it's just a 2D region because R2 was only 1D, right? Okay, so we can again visually get an idea of what the extrema look like rotating about. We can make a guess. Here's that intersection. It sort of dips down, so maybe here might be a min, or possibly at 0. It's hard to tell from the angle. Or maybe it does dip below. So somewhere around here might be a min. And then we can see pretty clearly that a max is going to be over here when x is 3. Y would be this -square root of 3. And we can get the corresponding z value. So we have a pretty good guess for both of these. And now we're going to figure that out algebraically. Okay, so first concept I wanted from this lesson was that we could visualize and use tech tools to help us visualize where these global extrema occur. And then we'll, in the next video, figure out how to algebraically verify what we visualize. And sometimes you don't even need a graph because, of course, we could do these same ideas in R4, R5, and even higher. Okay, one last thing for this lesson is we talked about the EVT over here. Well, we do have something similar in this section, and so I'll point out the page in the book here. We're sort of in the middle of chapter 2. We have the extension of the extreme value theorem. So the EVT is in this box on the EVT page. Okay, and so the conditions. If your function, z is a function of x and y, and it is continuous, so similar condition on some closed bounded region, R. Okay, so very similar conditions. So continuous function, okay, no problem what that means. You're just making sure you don't have any holes, gaps, jumps, asymptotes. So this one's totally fine because there's no denominators, square roots, anything that will cause those problems. And then closed, instead of interval, we now have to talk about a region like we have over here because this is a 2D region. So is this one closed? Yeah, it includes its endpoints. If the problem said something like this, and you'll see some examples in your journals of these, it's not completely closed, so you can't guarantee that there would be an extrema. And hopefully you see why that would be in Calc 3 visually, because you want to be that point up there. Let's see, we had one, yeah, when x was -2, we thought we had a guess that there was an extrema global max, but it doesn't actually exist because it doesn't take on that value. So you can get infinitely close to that point, but then there's a hole, a discontinuity at that point. You get infinitely close, and so we say there's no global max there. So we really need these things to be closed, which again, easy to check. This one's also closed. Includes all of its boundaries and endpoints. Includes all of its boundaries and endpoints. And then the second one was, so EVT here, f of xy this time is continuous. And the region R is closed and bounded. Okay, so we got closed down, again, includes its endpoints. Bounded just means the region isn't infinite. It means that you could put a lasso around it. The only way we couldn't put a lasso around a region if the region was all of the XY plane, right? So we don't do those kind of problems. We have to have some finite area that we're interested in. You can say, well, how useful is that, right? In a real life problem, you almost never say make 1 million of something, produce 1 million of this particular product, right? There's always some reasonable parameters for what X and Y could take on when you're trying to find minimizing cost or maximizing profit or any application. And so it could be really, really big. It just has to be finite, right? So that's all it means, is that your region doesn't have some infinities or minus infinities in it. So usually very easy to check these, and almost always holds, certainly always holds for like textbook problems, well-behaved problems. Okay, so then just like this one over here, it was just an existence theorem. If these two conditions hold, then you're guaranteed at least one global min, at least one global max. And you'll go through the journal and figure out why they're saying at least one. Just means that there could be ties. And hopefully you can come up with some visual examples, right? Maybe you can sit at your desk and make cloth over junk and just figure out, oh, if I just had like 2 apples under here instead of an apple and a tiny orange, then I could have a tie for the global max, right? So it's totally possible. That's why the at least comes in. All right, so let's just look at our example for which we want to, next video, actually find these algebraically. We visually got a pretty good hunch, and we want to verify that. Last thing, let's check that it's worth our while to go spend the time to try to find these extrema. And does the EVT apply for region 1? First of all, the function is continuous, check. The region is closed, check. Region is bounded, I can put a lasso around it, yes. For region 2, does EVT apply? Yes. Function is continuous, region is closed, includes its endpoints, and I can put a lasso around it, it's bounded. Therefore, it makes sense to spend my time hunting for these extrema because they exist.